Hello everyone, I'm Yifan from Carnegie Mellon University. Today I'm going to introduce our work on manipulation with shared grasping. Shared grasping is a grasping on an object formed by contact with both the robot and the environment. Comparing with grasping, shared grasping requires less contact points from the robot hand, so we can use it when a good grasp is not available. Unlike grasping, the object in a shared grasp may not be fixed. It can move flexibly by using the contacts in different ways. Shared grasping is an example of contact-rich manipulation. It is difficult to control because of the many possible contact modes. For example, in a planar system, every contact point has 4 possible modes. An unexpected contact mode usually means failure because different contact modes allow different motion. Unfortunately, it is difficult to distinguish different contact modes. A control law designed for one mode may bring the system into another under modeling uncertainties and disturbances. Robustness is important. So, in this work, we propose an algorithm to uniquely control a desired contact mode while avoiding others. We also propose a method to evaluate the robustness of a contact mode. We demonstrate our method in several examples. The algorithm starts with a modeling method that can distinguish different contact modes. Contact forces on an object form polyhedral convex cones in the object range space. If a contact mode has force balance, the cone formed by hand contacts and environmental contacts must intersect each other. We call this intersection the cone of the mode. It represents the set of wrenches that the robot may possibly apply in this mode. For example, here we show the 13 non-empty cones for the hand block system. Since different modes have different cones, we can select a mode by applying a wrench in that cone. However, this approach is not robust because different cones are close to each other. For example, if we apply this wrench to obtain the FSFF mode, a tiny disturbance force can move our wrench into the cone of another mode. To resolve this sensitivity, we cannot use force control only. Instead, we use hybrid force-velocity control, which does force control and velocity control simultaneously in different directions. We use hybrid servoing algorithm to find the velocity control, so it is always compatible with our desired mode. Then we can eliminate contact modes that are not compatible with our velocity control. The remaining cones are better separated from each other. But still, we cannot put the force directly in the desired cone because we cannot control the force in the velocity-controlled directions. This is a limitation of hybrid force-velocity control. However, since the actual wrench must be within one of the remaining cones, we can project all these cones into the force-controlled subspace and pick a wrench in the projection of our desired cone while staying away from the projection of other cones. This way, the desired mode becomes the only possible mode, and we don't need to compute the uncontrollable forces. This concludes our algorithm design. We call this algorithm wrench stamping because of the wrench cone projection. Using wrench stamping, we can reliably control different contact modes without worrying about the mode ambiguity. Next, we propose 2 stability margins to evaluate the robustness of a contact mode against 2 types of failures. The geometrical stability margin measures how likely it is for the cone of the mode to disappear under modeling uncertainties. The control stability margin measures how hard it is for disturbance force to move the wrench out of the desired cone. We can use the stability margin to select the most robust contact mode for challenging tasks. At each time step, the user only needs to provide the desired velocity. Our algorithm selects the contact mode and computes the control to maximize robustness. We can also use the stability margin to find good finger placements by optimizing the contact geometry over the geometrical stability margin. This approach further improves the robustness of the control. In this example, the same controller works for objects that are different in shape, weight, and friction. To summarize, in this work, we introduce shared grasping as a flexible and reliable way of robotic manipulation. We provide methods to control the shared grasping system and to evaluate the stability of a shared grasping system. We demonstrate the capability of our method in several representative applications.